Hey guys, welcome back to Luke's Math. Today we'll start by looking at the exercise I gave to you all last video. So in this exercise we're looking at a kid who's playing Pokemon for the first time. He's selecting his starter Pokemon at random, and there are the three possible choices, so Bulbasaur, Squirtle, and Charmander. First step is going to be to create the sample space. Okay, so the sample space is, remember, the list of all possible outcomes. So what are the possible choices he has? Well, it's pretty simple. It's just three: Bulbasaur, Squirtle, and Charmander. Okay, next, let's move on to B, where we're going to list all possible events. Remember, the events are the all possible events are the all subsets of the sample space. So we're going to take our sample space and find all the various subsets. So we'll start with the first three, which are just the individual Pokemon. And these right here are our elementary events, right? They only have one possible outcome. Okay, next we're going to do combinations of them. So we read these as like Bulbasaur or maybe Squirtle. So this event would be if he were to select Bulbasaur or Squirtle. The next one would be Bulbasaur and Charmander. The next and last one of the two would be Squirtle and Charmander. Okay, and there are still two more sets, but these are the trivial ones, right? We could have the whole sample space, so if anything occurs in the sample space, then that's that event. And we also include the empty set, which is the always a subset when we look at various sets. And so you might have learned in your set class or wherever you learned some of the notation and terminology behind sets. An easy way um, to find the number of sets, subsets, just to make sure you're getting all of it, is, well, if we know that the order of a set is some number k, and then I'm going to use some notation here, is going to be the number of subsets, though. What's important right here is that the number of subsets is 2 to the k, so 2 to the order. And that makes sense, right? What is the order of the sample space? Well, there's three different options. So the number of subsets would be 2 to the third power, in this case, 8. Okay, let's wrap this problem up with C. We're looking at which events are mutually exclusive. I'm not going to write out all of them, but basically when we take the intersection between the two sets, we get the empty set. So an easy one to start with is we know that the elementary events, so B, S, C, are pairwise mutually exclusive. Okay, so that automatically gives us three separate pairs, and then there's three more that are mutually exclusive, but I don't want to write all of them out, so you can fill in those gaps as we go. But we do know that the elementary event Bulbasaur intersected with just Squirtle and Charmander because this one doesn't have Bulbasaur in it. This is equal to the empty set. And you would do this for three more. So just take the Squirtle and find the set of two that intersects. Okay, so let's get into today's discussion, which is on probability. So probability, what's most important is that it's a set function. And we're dealing a lot with sets because we have a sample space, which is the set of all outcomes, right? And then we take events, which are subsets of those outcomes. So when we ask for the probability, we're asking really for the probability of a set. So you take a set as your input, and you're going to output a numeric value. Okay, probability is a set function. Let's be more specific about that. We also denote it as the probability, in red, probability of some event A. Let's get more specific with our definition. Okay, and we're defining probability set function. Okay, so this is going to be a bit of a long one. Let S be a sample space. Okay. And we have a set number of events. So A1, A2, A3 are possible events. And the number of possible events, we just said it was 2 to the k, but that's for a finite sample space. If it was a infinite sample space, then we would correspondingly have infinite number of events. Okay, now here comes the definition. So we say then the probability of A is, well, I guess P of A is the probability of A if the following hold true. Okay, 1. First condition. The probability for some event is always greater than or equal to 0. Just means it's non-negative, right? And this is for all indices, so all I is in the natural number. Okay, that's important. We don't want to have a negative probability. Next, the probability of the sample space is equal to 1. This saying, like, the probability that something occurs within the sample space is 1, which should make sense, right? It's 100%. The probability that we get an outcome from a trial should be 100%. And that means also, well, we'll get into what that means, I guess, in a little bit. Consequences of that. Next one is that the probability of the union of all events is equal to the sum. I messed that definition up. My bad. Let me erase. Is equal to the sum of all the probabilities of those events. So this, where this is, oh, sorry. And then we also need to make real careful note. This only happens if our events are pairwise mutually exclusive. Okay. That's our definition. The reason for it being important that it's pairwise mutually exclusive is because if we have some overlap, we're going to be double counting probability. And I think we're going to go into that in the next video when we discuss more properties of the probability. But this is an interesting and important result because this says if we can take elementary events, right, so it's just one specific outcome within the event, we can add all the probabilities up and they should sum to 1 because all the events in the sample space, right, so the union of all events, of all elementary events, should turn out to be the sample space. Okay, so maybe I'll write that out. So example 1. Oops. Example 1. So if A1, A2, A3 are elementary events and they're different. I guess I should say they're different events because if they're the same event, then it wouldn't quite work out. Then if we sum the probabilities, a sub I, oops, we're summing the probabilities, not the events. Can't sum an event. We sum the probabilities because the probability is a real number. It should come out to be 1. Okay. And we're going to use that result, I think, later on as well. Okay, so let's get into another example. Before we get into this example, based on the definition I wrote, there's another model that's sometimes used, and I think the textbook that I reference uses it in a bit. It's the classical probability model, which is definitely more of an intuitive sense of probability, right? Where it's like you have, okay, the probability of something is the number of ways it can occur over the total number of possible outcomes, right? So it's like, okay, what is the probability of rolling a 6 on a 6-sided die? Well, there's only one way that can occur. You roll a 6, and there's 6 total possibilities, so the probability would be 1 over 6. So that's the intuitive sense of probability, and we're going to use that as well, but I didn't feel it was worth writing. Okay, so the next example is to roll a 4-sided die twice. First, let's list the sample space. So for the sample space, I'm going to denote it as an ordered pair. So the first entry in the ordered pair will be the first roll, and the second entry in the ordered pair will be the second roll. The easiest way to do this, I think, to make the sample space would just be to do a table where, like, on the left-hand side we have the first roll, or sorry, on the column here we have the first roll, and on the row here we have the second roll. So there's 4 options. You can get a 1, 2, 3, or 4. So the first roll would be, the first option is you get a 1 on both one. This choice right here would be getting a 1 on the first roll, 2 on the second, 1 on the first, 3 on the second, 1 on the first, 4 on the second. And then you'd keep going to fill this in, right? And the last one would be 4, 4. Okay. So those are the total outcomes. There's 16 possible ones, right? It's a 4x4 grid. And then what's nice about elementary events is, in this case, they're going to have the same probability, right? There's an equal chance that I get every single one of these. So what we can say, using that more intuitive classic probability model, for an elementary event, the probability that we get some outcome I comma j is equal to 1/16th, right? And this is for all I and j as long as they're within the possibilities of what we can roll. So this is for I comma j is an element of the set of 1, 2, 3, 4. Okay. And this isn't always going to be the case, right? There's going to be some models maybe we look at where an elementary event, there's different elementary events, but they're not going to have this, they're not equally likely. This is a special case where for any elementary event we can come up with, where we only have one outcome, it is equally likely as all others. Okay, let's keep going. Let me come up with some events, and then I'll have you maybe pause the video and try to see if you can find the probability of each of these events. So the first one is event A, being that the sum of I, so I is the number on the first roll, j is the number on the second roll, is equal to 3. Whoa, that's not a 3. Okay. Event B will be the first roll is a 2. And then C, let's do, how about for C, both rolls are the same? Okay. Pause the video, maybe see if you can figure out what the probabilities are. Let's go ahead and describe what event A looks like. What are the possible outcomes in event A? Well, the sum has to be 2, or sorry, the sum has to be 3. And there's only one way. The only options we can do are using numbers 1, 2, 3, and 4. There's only one way to do that, is if we add a 1 and a 2 together, right? So the only outcomes are, maybe we get a 1 on the first roll, then we'd have to get a 2. And the other one would be a 2 on the first roll, and a 1 on the second. So those are the only possible outcomes. And so our sample size, there's 16 total outcomes, right? And then in this case, event A has 2 possible ones, so the probability that A happens would be 2, since there's 2 ways event A occurs, out of 16. So this is equal to 1 over 8. Okay? And again, this is a special case because all the elementary events are equally likely to occur. So in this case, we can say, okay, well, the probability that I get a 1 over 1, 2 is just 1/16. The probability that I get 2, 1 is 1/16. So combine those two, they're different events, they're mutually exclusive, so I can add them together using the probability rule, and we're going to get, well, 1/16 plus 1/16 should be equal to 1/8. Okay, let's do B. So B says that the first roll is a 2. Okay, well, there's only 4 different ways to do that, because the first roll has to be a 2, so we're set in stone on that one. The second roll could be whatever, so we'll account for all those. I'm not going to write everything out, but there should be 4 different options, right? 2, 1, 2, 2, 2, 3, 2, 4. So what is its probability? Well, it's 4 elementary events, 4 mutually exclusive elementary events. So we're going to add them all together. And so that should be 4 over 16, or in this case, 1 over 4. Okay. C. C is that the rolls are the same. So it's either a 1, 1, 2, 2. They just have to be the same number. 3, 3, 4, 4. Okay. And then what's the probability of this? Well, there's 4 mutually exclusive elementary events. So the probability that C happens would be 4 over 16, or in this case, 1/4. Okay, and then we can mess around with some of these. I like using intersections and unions. So if we look at the probability that A intersects B, well, what do they have in common? Let's look at what we've described. The only thing they have in common, I think, because A needs to be 2, 1, needs to have a 1 and a 2, so the only thing they have in common are the 2, 1 roll. So if there's only one way A and B both occur, well, we're really looking at just the probability that that happens, so the 2, 1. And so it's the probability of one elementary event, and in this case, the probability of any elementary event is just 1 over 16. Okay, let's do one more. We can look at the probability of A intersect C. Well, let's see what A is, right? A is 1, 2, or 2, 1. And C says we need both rolls to be the same. Okay, so what is their intersection? Their intersection is just the empty set. And here's another rule. I think there's a formal proof maybe in the book, or maybe that's left as an exercise. Either way, there's a formal proof to show that the probability of the empty set is 0. And we can think about that intuitively, sort of, right? What is the probability that none of the events occur, I guess is the way of thinking of it. Well, that would have to be 0, right? If we're rolling the die, if we're doing a trial, if we're performing the experiment, right, there must be some outcome. Okay. That's it for all I have for this video. I'll leave you guys with the practice problem to try on your own, and we'll go over the solution in the next video. Okay, here's the problem for you all to try on your own. I'm going to ask that you find the probability of events A, B, and C in each assumption, given that when the experiment is performed, we know that only one of the events will occur. So what does that mean? That means they're mutually exclusive, right? Because we can't have two events occurring, meaning that the intersection must be the empty set. So they're mutually exclusive events, and we're guaranteed to see at least one of them when the experiment is performed. So start by looking at the case when all three probabilities are equal. The second case when probabilities of A and B are equal and the probability of C is equal to exactly 50%. And in the last case when the probability of A is equal to 2 times the probability of B, which is equal to 3 times the probability of C. Okay, try that on your own. I'll give the answer at the start of next video.